right. It's 40 after, so let's get started. Everyone's aware there's a final in a couple weeks. What is it, on Thursday? Yes. So I will not be here next week, but I will be here the Monday following for 2-hour office hours if people have last-minute questions on Monday. So Monday from 1 to 3 in my usual 229 Burge Hall office. Bless you. Let's see. All right, what else? What else do I have to tell you? So today my goal is just to answer any questions you have about the final and to just give a quick review over what you've seen in the class so far. And yes. There are reviews. There are review sessions held led by GSIs, and the GSIs have office hours. There's plenty of stuff going on over the next week to prepare for the final. But I'm out of town, unfortunately, so I won't be with my usual office hours. But as I said, I'll be back on Monday the following week, and I'll answer questions from 1 and 3. You can email me too, although I get lots of emails, so it's always better. Chase down a GSI and get answers in person. It's a little better. And also, lots of students are swimming in office hours now, and it becomes clear when we're trying to solve some thermodynamics problem that the real problem they're having is they still are not comfortable with free body diagrams. The final is cumulative. Make sure you're comfortable with stuff you've seen earlier in the course. Even problems that aren't explicitly about earlier material are implicitly about earlier material. The better you are with that stuff, the better off you'll be on the new material as well. The final's going to consist of 6 problems. You've seen a bunch of example test problems from past years. I've got them up on the website. They include they're pretty representative of the kind of distribution you're going to see, of the kind of problems you'll get on the final. Mostly new stuff, but there's a lot of mashups, right? The problem is ostensibly about thermodynamics, but then inserted in the middle there's going to be an oscillation or something, and then maybe a little bit of waves thing at the end, right? There'll be a Doppler shift problem inserted in this other problem. You may not recognize it as a Doppler shift problem anyway. So be good at recognizing and collision. Be a collision in a problem, right? Oh yeah, what's conserved? Can I use momentum, kinetic energy? Oh, bless you. Lots of Simon's sneezing a lot too, but the allergies been killing me this last week. So I'll apologize in advance if I start coughing away through the lecture. So let's see, what else can I tell you? And before I start getting into topics, just a little more about the business of the final. You have one, just like with the second midterm. You get one sheet of paper 8.5 by 11 or smaller. You can write whatever you want on both sides, and that you can use that for the exam. Be smart about it. Make sure you've got things that you need on there and not lots and lots of extra stuff, right? And one last thing I'll say about preparation, no calculators, sort of the usual drill. One last thing I'll say is that a lot of students have been coming to me saying, what's the best way to prepare for the final? And my answer is as always, the best use of your time is solving specific physics problems. So, rather than reading the book over and over and over again, underlining passages for any physics class, you're best off choosing specific problems, trying to solve as much as you can on your own, then going to the reading in order in the service of solving that problem. Going to GSI office hours or mine on Monday or whatever, and getting help, but getting minimal help, just one hint to help you get past that hurdle, right? That's the best way you can go about improving your ability for the final. And the kind of problems work on, I think the practice tests are probably the best things, but what you see is, of course, going to be different in detail. But that's the right character of the kind of problems you'll see. All right, what else is there? Test rule, yeah, 10. Okay, I think that's all my business stuff. Yeah, there's 6 problems on the final. They're a little bit longer in some cases than midterm problems. So the test is like, it's like 1.5, a little more than 1.5 times as much material as one of my midterms. Okay, so first of all, what's the old stuff you already know? You already know, I'm not going to write these things down, I'll just rattle them off. You know Newton's second law, you know Newton's third law. You know how to apply those, and you know when to apply them, right? You're going to have problems where you're going to combine those with Newton's second law for rotation. So, you need to do these things. There's an X equation, a Y equation in general. You've got 3 equations right there. Sometimes if you're smart about the choice you make for your pivot point, right, you can get away with just this and you can solve the whole problem. Remember, whenever you're applying this and you're calculating torques, right, and all these things, yeah, torque might show up on the final. I suspect there'll be a torque or two someplace, not as the major thing you're being tested on. So just make sure you remember what that is. Make sure whenever you calculate that, you know what the pivot point is or something. You know what pivot point you're choosing, in other words, for your torque. You know what your convention is for positive rotations and positive torques, right? Make sure you're explicit about that to yourself and to the grader. Make sure use free body diagrams, right? And for that matter, don't just if you've got a problem where you've got torque going on, don't just do your forces like this. This is a fine thing to do first. But make sure you draw the extended object and indicate where they're on there. So stuff you know. So where it's acting as well as what direction it's going. I still see students in office hours who aren't comfortable with this. That's just random. But you get the idea. You want to indicate where the force is acting and what direction it's acting. So this is all old stuff. Remind yourself of the kinematic equations. Maybe write them down. I don't know if you'll need them or not. But there are ways to solve problems that involve them, and there's other ways that don't. Just gives you more flexibility if you've got all that at your fingertips. For circular motion too, right? If you've got a circle, you got something going around. Bless you. Something going around in a circle, right? And what is the acceleration of this guy going around in a circle? So suppose he's moving at some velocity v, and I want to know and he's moving, let's say, at a constant speed, and this is some radius r. What is his acceleration? Yeah, it's v squared over r. If he's changing his speed, then this isn't the full acceleration, it's only the radial component. And which way is the point, in or out? I drew this as my radius r, then I wrote a sub c, but looks like I'm indicating that that's the direction of the acceleration. Does the acceleration point toward the inside or away from the middle of the circle? Yeah, toward the center. So I shouldn't label it like that, I should say this. Here's my acceleration. Anyway, yeah, you got it. So just remind yourself of those things. Newton's third law, equal and opposite forces, right? For any what is that? Force A on B, well, there's going to be a force B on A. All right, and then what else? In terms of torque, yeah, know your pivot point, know your convention for this. Also, when you think about moments of inertia, yeah, I might as well write down your parallel opposite. I'm just giving you everything. I'm not sure. I haven't written the exam yet. But if you have a problem where you use the moment of inertia, say for Newton's second law for rotations, right, where you're relating the net torque, right, times I times alpha, just make sure that you're consistent. Whatever pivot point you use for torque, you better use the same pivot point for your moment of inertia. And if it's not the center of mass, that's easy. Just do this, right? It's a d squared, m times d squared. Just make sure you use the parallel system. All right, bunch of stuff. You may have problems when there's more than one object tied together. I don't know, some of the past finals included things like that. In that case, you have to worry about relating the accelerations of the 2 objects. You have to worry about, like something like this, right? You got some pulley, there's a mass hanging over here, maybe this is mass 2, and then there's some, you see things like this, right? If you have a problem like this, you want to be able to relate the 2 tensions. If this is an ideal pulley, ideal rope, the tensions are the same. If not, then that's not true. This tension can be different than that tension. But if that's an ideal pulley, it's an ideal rope, T1 equals T2, right? If you know the acceleration of his center of mass, right, then you can relate that to the acceleration of this guy in the downward direction, right? Because they're tied together. In this case, I tied it to the middle of the wheel. So it's just his acceleration that way equals his acceleration that way. With no numerical factor in there, other crazy business, right? If the rope's coming off the top and you have to think about it, then you get a factor of 2, right? Because the center of mass only moves half as far as the top of the wheel. I should say it this way. The speed of the top of the wheel is twice as much as there. Anyway, last in the past, you guys all know that. But that's just to remind you of that. One more thing is how to relate the angular acceleration of this wheel to the linear acceleration at center of mass. Well, if that's my x direction, I could say, the acceleration of object 1 in the x direction, that's just going to be whatever the radius of that wheel is, right, times the angular acceleration of the wheel. And to get my sign right, I go, I got to make sure the sign's right. If that's my positive convention, if that's positive x direction, then yes, I got the sign right, that's plus sign. All that stuff, bunch of stuff. All right, so let's see, how far am I? Just going, yes, and potential energy due to gravity, potential energy for a spring, these are useful things to know. we have any other kind of potential energies? I guess, well, when we get to fluids, I'll talk. So in the new stuff, I'm going to slow down and go talk about the new stuff in a few minutes. But before we get to fluids, we've got potential energy due to springs, right? Potential energy due to gravity, right? MGH, right? Potential energy due to spring. What's that? It's 1/2 K. There's lots of K's in this class, right? There's the spring constant times or delta x squared. And potential energies, when you have potential energy due to a spring with this particular formula, it's important. Sorry about that. It's important that delta x equals 0 is the equilibrium position, right? But over here, potential energy due to gravity, it's your choice where you make the 0 point for potential energy due to gravity, right? Wherever you want, but just stick to your convention, whatever it is. Let's see, what else did we cover before? Yeah, we did. That's right, kinetic energy, the kinetic energy total, it breaks up into pieces, right? There's kinetic energy of the center of mass, plus the kinetic energy due to internal motion, which in our case was almost always this rotation about, right, center of mass, right? So in that case, you'd say, oh yeah, that's just, what is this? That's just 1/2 mv squared. What v? The velocity of the center of mass, right? And then this thing is 1/2 I omega squared. And it's important that this moment of inertia is about the center of mass, right? And you can also write this other ways. You can just write this as 1/2 I omega squared, where I is about any stationary, about the stationary point, if the thing actually has a stationary point. But I'll just leave it like that. You can write it the way if you like to. All right, conservation. Yeah. So obviously, a really useful concept for the probably is going to show up in the final in a couple different ways, right? Conservation of energy, also conservation of momentum, right? Knowing how to use those, knowing when they're, and also if you notice a collision on the exam, if it's elastic, what's conserved? Kinetic energy is conserved, right? You have an elastic collision. And is momentum conserved for an elastic collision? Yeah. Is momentum conserved for an inelastic collision? You bet. Momentum's always conserved. Total energy is always conserved. It's only kinetic energy that's not conserved. So yeah, just jog your memory on all that stuff. Okay, fine. What else? Anything else to this? Oh yeah, definition of power. You have to know what power is, right? How much work per time, right? This is instantaneous power. Average power, just put deltas in instead of d's, right? It's just how much work you performed over some finite length of time. Great. And the definitions for work and impulse, you know what those are. Work is if you have a constant force, it's just F dot whatever your change in position is, right? I say constant because I didn't integrate, and then I have to integrate if the force were changing over that distance. And then for impulse, right, it's the force times the change in time, and that's all. These are both assuming constant force. You need to put an integral there if you don't have constant force, but yeah, constant force. Anyway, very good. So you know all this stuff. You've learned a lot of stuff. You've covered a lot of material in this class. Hundreds of years of deep thinkers produced all these facts that we crammed into one semester. So all right, what about new stuff? So first thing we did was oscillations, right? Oscillations, we've got just a few equations. There's not that many equations. You have extra variables. It's sort of redundant. You have more variables than we need, but they relate to each other in a pretty straightforward way. So what is F? F is the frequency in terms of cycles per second, not radians per second, cycles per second. It's 1 over the period, right? It's not tension, it's period. We can rewrite this thing in terms of omega. I know F is proportional to omega. This is radians per second, right? Although we don't utter the radians part when we're comparing units in an equation, but we remember that's what it represents. And I need an extra 2 pi someplace. Does the 2 pi go in the numerator or the denominator over here? So is omega going to be bigger or smaller than F? How many radians are there in one cycle? 2 pi. Is 2 pi bigger than 1? Yeah. And so yeah, that means that it's like 6, right? So bigger than 6. So that means that omega tends to be a bigger, well, it is always a bigger number by exactly 2 pi than F. There's more radians in a cycle than there are cycles. Well, there's more than 1 radian in a cycle. That means that if this is a bigger number than that, I better divide by 2 pi. Did I get that right? So if when omega goes from 0 to 2 pi, F, yeah, that makes sense. I think that's right. So I'm just thinking through where the thing should go. But you also have it written down so you won't get confused. Let me just make sure I've got so it agrees on my sheet. It does on my little cheat sheet. See, I know I'm allowed to have 5, and you guys don't. Yeah, actually, so I had plenty of exams in the past where I was allowed to use the whole book, and it didn't do most students any favors because they wouldn't prepare a sheet ahead of time, and they would be searching for the entire exam, trying to find that magical formula, and they would not get through the exam. But other tests were allowed to bring any sheet in at all, and those were that's why I really learned my physics. I had to figure it all out because I have no memory whatsoever, as you've noticed as I've taught this semester. So I had to figure things out by the few things I could remember and sort of triangulate. You actually know lots of things that are complementary in a way. You can use them to triangulate on the right answer. You can check your answer in various ways. So you should constantly do that. You see all the mistakes I make on the board in class, and with your helpful raising hands, and also just checking units and checking signs and checking the limiting cases, I can make sure my answers make sense. So just don't forget to do that on the exam. So let's see. Oh yeah. So if you have an oscillator, you have some mass on a spring. One thing we can ask is, what's the total energy of some oscillation, right? There's a couple ways to calculate that, but in general, for any given moment in time, the total energy is just going to be, right, for an oscillator that's oscillating back and forth at some frequency, and well, let's do it this way. At some moment in time, it's got some velocity and it's got some displacement x. Well, the total energy is just going to be 1/2 mv squared. That's just kinetic energy, right? Plus the potential energy that's in the spring at that moment in time. 1/2 delta k times delta. Well, I'll just call it x, but you can also think it's delta x. Just remember that x right there better be defined so that x equals 0 is the equilibrium position of your spring, right? When the spring is unstretched and uncompressed, where it's exerting a force. So that's your total energy. If you want to calculate it, and you know what position this guy's at, when he's not moving, say, oh, that's going to equal 0. That term goes away, and then this is just delta x is the delta x max, right? Or if you like, it's the amplitude of the oscillation. So you can say, oh, it's 1/2 k times a squared, where a is the amplitude. That's when they calculate the total energy in the system. But if you know how fast he's moving right at the equilibrium position, that's equal to 0. Anyway, you get the idea. But at any moment in time, you can, because of conservation of energy, those have to add up to the total. We learned a couple formulas. So what do I expect on the final? I don't expect you have to rederive, say, this formula. It's perfectly fine for you, if you know the answer, to say, okay, I've got some oscillator, some mass on a spring. I know what the spring constant is at this stage and what the mass is. Perfectly reasonable if you say, oh, great, I can figure out then, I know what the formula is for the frequency. I know it involves k and m. I know that the stiffer the spring, the bigger the frequency, the bigger the mass. We don't have it down. You can think about it right now. All right, so that must be right. I'll even check. Oh, it's right. Thank goodness. Got the right units. So you can just use this without deriving it. Is what I'm trying to say. But I would say at every stage, let the grader know you know where this came from. Right? This is like, oh, this is a simple harmonic motion, or simple harmonic oscillator, or something. Let them know what does this represent? Where does it come from? And don't get confused with the different notions of omega we've got in this class. This is the oscillation frequency in radians per second, the angular frequency of oscillation of some mass on a spring. But what if you have? We talked about this a couple of lectures ago. How you've got like maybe 8 different ways to solve a problem that involves the thing you're being asked. It's a simple pendulum where you've got Tarzan at the end of a rope or whatever it is, chandelier, or whatever this thing is. Some mass here, some length here. Well, thinking about it in terms of an oscillator is the right way. If you have enough information to know how high he started or what his velocity was at that point or whatever. Maybe he's not moving and he's at this height off the ground. You can use conservation of energy to figure out how fast he's going at the bottom. But you can use a similar equation to this to figure out how long it takes. But then you have to think you need a formula for a frequency that's correct for a pendulum. And once again, it's similar to this, right? But now there's no mass at all, right? It's bigger with g and smaller with L, right? Is that the right units? Meter per second squared. Meter, yeah, 100 second squared. That's 100 second. That looks good. So it's okay to use this out of the box as well, as long as you're clear on why you're allowed to use it. There are other types of pendulas, though. Pendula, I guess, for plural, that aren't simple. This is simple because there's just a rope here that's massless. All it does is make sure it constrains this mass to move along in a circle. All the mass is right here. If you have a pendulum that's more complicated, you got some crazy shape, right? And there's some, so you got a pivot point up here, right? This is where it's pivoting. Some nails through it up here, and maybe the center of mass is down here someplace. Well, this right here is the length that matters. The length from where the pivot is to where the center of mass is, that's the length you want. But you still can't just plug directly into this because this formula, when we calculated this, we put in information about exactly what the moment of inertia is of the system about this pivot point, and it was a very simple relationship in terms of L and M, right? So then it turned out that everything canceled, we got a simple formula. In the more general case, you get something that reduces to this, but it's got mgl in it, and then on the bottom you've got I around the pivot point. So this is the moment of inertia, but it's about this pivot point, very important. Not the center of mass, about that pivot point. And that mass right there, so now mass is explicitly appearing inside the formula, right, for omega. But the reason it goes away over there, right, oh yeah, is because when we calculate the moment of inertia about this point, it's just proportional to the mass. That's why it cancels out. So anyway, all right, oscillators. Also, one more thing I'll mention about that, you can have a torsion oscillator, right? Whenever you've got a force that's restorative, that's linear with your distance from the equilibrium point, which can happen in any kind of in a lot of situations. In fact, it happens in almost all situations. If you've got a mass on a spring is the obvious one, but I mean anything. If you have I don't know, just a piece of wood in the water, right? And that's a situation where you push it down, it wants to go back up. If you lift it up, it wants to go back down, right? It's a restorative force. There's lots of examples of oscillators that aren't explicitly listed in this short list of the kinds of things you might see, but a torsion oscillator is one where you twist it that way, it wants to twist back, twist it this way, so it has a restorative torque instead of a restorative force, right? And what does that look like? That has an omega that has a frequency that's very analogous to the one we have up here. Instead of k, you've got kappa, which is the proportionality constant between the torque and the angular acceleration, right? So it plays the same role that k does. And then at the bottom you've got I, your moment of inertia, instead of having mass, your sort of your rotational analog for mass. Anyway, all right, oscillators, right? I didn't draw any pictures of oscillations. You should be comfortable with that. You should be comfortable with this kind of stuff. Here's the amplitude, right? You should know how to relate all the different properties of an oscillation. There's no wavelength with oscillations. There's an amplitude and there's a period, right? This would be the period here. I must be plotting times. I told you it was an oscillator. This is some other variable. I don't know, x, y, whatever it is, right? But when we get on to waves, now you have to worry about space and time, right? So all different. I'm just racing through stuff here. Do you have any questions? People have questions about oscillators? Is there anything that bugs you about oscillators? No? You love them? Good? No. Like it's a general dislike. There's no specific question. All right. Waves. What about waves? Waves, again, energy is transmitting down some object, well, either along a rope or sound waves in the room, whatever it is. There's longitudinal waves, there's transverse waves, there's standing waves and traveling waves. So what do I expect you to do? I expect you to be able to figure out how to fit standing waves into some physical situation. If you've got, so this is my oscillator, I'll just plug it like that. So in terms of waves, right? Well, here, first let's do the traveling, and I'll say something about standing waves. I think what I'm going to say, though, I'm just going to say that wave speed, you know how to calculate that? That's just how far you go, the wavelength of the wave, divided by how long it takes you to get there. That's one period, right? We can rewrite this. Just check and make sure I got my 2 pi's in order. But of course, I just avoided 2 pi altogether because f is just 1 over t. There's no 2 pi involved, right? Lambda is still the same, great. So 2 pi's come about, and we get into k's and omegas, right? F is the same thing as what is that? That's 2 pi omega, but then lambda is 1 over 2 pi times k. Oh, what did I say? So omega good. And times k. So in the dust layers, I think you just get omega for this guy. I think you get a k in the bottom, right? And I think 2 pi's cancel. Is that all right, everybody? So you should be comfortable with all that kind of stuff. All you need is a few of these equations right now. You can get all the rest of them from those. Just be careful with your algebra. Make sure I'm not lying to you guys. I think that's right. K does have to go down here because that goes like 1 over distance, right? And just to make sure this thing has we got a 2 pi in front, we got 2 pi in front. Good, looks good. So that's wave speed, right? We can also talk about how fast a piece of the rope is moving, and then you have to think in terms of that little oscillator. Those are different speeds, right? The speed of the piece of rope right here that's wiggling up and down, as opposed to the wave speed. Yeah.
I think earlier you said that the oscillators don't have a wavelength.
Oscillators don't have a wavelength. All I meant by that is that if you have an oscillator, it's just moving back and forth. It has an amplitude. So there is space in this thing, this oscillator. It's got some displacement as a function of time. It's sinusoidal, right? But it doesn't have a wavelength in that. So if I have a bunch of oscillators, they're coupled together. If I've got a rope, if I've got a bunch of air molecules in a room. Now the wavelength is talking about distances that are, well, I want to say they're very long. That's true. They're typically very long compared to the actual displacement. Your rope's displacing up and down like this, but the wavelength has to do with the shape of this wave in any orthogonal. Well, if it's a transverse wave, it's orthogonal direction. If it's a longitudinal wave, it's in the same direction as the oscillation's moving. But the wavelength is a description of what phase the oscillators are in as you move along the direction of the wave's motion. It's not a statement about how far an individual oscillator moves as it goes back and forth in its little wiggles, right? So this guy's going up and down. He's moving. He has an amplitude right here, right? Of whatever that. I started to do this. There we go. He's got this amplitude, but there's no wavelength. This oscillator's motion doesn't have any wavelength associated with it by itself. You have to know something about the coupling between it and the other oscillators, the other bits of rope that are oscillating up and down. But of course, they're coupled together because they're tied together. The rope's all connected physically, right? So what happens is, this guy's up, this guy happens to be down, happens to be up. That's how far you have to go to get to the same phase of oscillation. They're both up. That's your wavelength, independent of how far he moves along here. Same thing for sound wave. Even though it's in the same direction, they're 2 different lengths: the amplitude of the oscillation and the wavelength of the wave. It's made up of many oscillators, right? So here's how we get our wave velocity. We calculated several formulas for different types of waves. We didn't do ocean waves. We talked about waves on a rope and waves on